Greetings, ladies and gentlemen. Today we will take you along our trip as you discover the research we have been working on in climate and comfort. Thank you for watching. The purpose of the study is to design a modular and prefabricated building in a site and country of our choosing.
In this presentation, the emphasis is on kinetic facade, which is by definition about using geometric transformation to create a motion or movement in a space. In our project, this is explored further to achieve sustainable design in response to the environment, further evaluated by IES simulation.
In this video, we will start with site study, concept design, IES analysis, green star rating, and life cycle analysis.
The following items shall be studied in IES software.
The site we have chosen is in District Waterloo, Sydney, Australia. Sydney belongs to climate zone 5 and has a temperate climate, with its summers reaching 26 degrees and winter 8 degrees.
The iconic buildings in Sydney, such as the Sydney Opera House, Sydney Museum, Sydney Fish Market, and the Sydney Harbour Bridge, consist of curvatures as a link to Sydney's oceans and its harbours.
Let's move to the site analysis.
The empty site seen here is selected, which is within Waterloo of Sydney, Australia.
The site selected in Waterloo is in between two main roads. It has a close proximity to libraries, bus stops, educational areas, parking areas, and parks, which will allow us to gain points in Sustainable Site category in the Green Star assessment. It is important to note that Australia is in the southern hemisphere and therefore receives direct sunlight from the north and diffuse from the south.
Moving to the design concept.
Our concept design is derived from sperm whales, which is popular and lives mainly in Sydney's oceans. Whales are also important tourist attractions, as many take cruises out to the sea for whale watching. Biomimicry design is a practice that learns from and mimics strategies found in nature to solve design challenges. In using the biomimicry approach, we have considered the cross-sectional views of the whale to derive our building form and modular system. By taking the form of the whale, our concept design is inspired, as seen here.
As you can see here, this is the plan of our museum. The entrance of site is from the north. It is an open space consisting of two different levels with having the exhibition in the middle.
Our building is a maritime museum exhibiting ancient boats, artifacts, and fish tanks intended to raise awareness on the ocean species.
Our building design is developed according to the minimum requirements of Building Code of Australia. R&U values are extracted for glazing, external walls, flooring, and roof.
However, upon conducting solar gain and air temperature analysis, once applying the kinetic skin, we have found no improvement in solar gain and an increased air temperature, giving us opposite effects. This caused us to go back and minimize the number of openings in our building and conduct the same test. The results found for the base case were positive. There are considerable reductions noted once we have reduced the glazing by approximately 58%. This base case we will use for applying the kinetic skin and assessing in the Green Star rating system.
Our form consists of small sections that will join together and kinetic skins applied on the east, west, and north.
The kinetic facade is acting mainly as a shading device that moves, shifts, and transforms depending on different climatic conditions and times of day. Our main kinetic skin is modeled with Grasshopper plugin, as seen here. The intention is to create a facade movement which embodies an atmosphere relating to the ocean and fish fins.
Moving to the construction method.
The building external walls is by Steel Master Supplier. The steel frames are made of 80% recycled steel and are covered in Galvalume plus coating. As a result, we are creating an architecture popularly known as Quonset huts that are a lightweight, prefabricated structure of corrugated steel.
The mechanical system of the kinetic facade consists of linear actuator. To support the north shading mechanical system, slider crank mechanism used.
Next, IES analysis.
For the kinetic skin as an energy-reducing strategy, the first analysis studied is solar gain and air temperature with the HVAC turned off.
To verify the results of our finding, our building with its kinetic skin is compared to the base case, which we refer as improved case. The improved case consists of the following. First, material with a lowered U value, and second, applying kinetic skin.
Our building construction template was developed based on the minimum requirements for U and R values found within the Australian Building Codes.
The next strategy is selecting best building orientation. Determining the best building orientation on site is based on the lowest solar gain energy on the building, which was found to be at 270 degrees north.
After applying the kinetic skin in the north, east, and west facades, where we have found getting the most solar gain energy, the same was reduced drastically. The strategies of the kinetic skin are determined according to the azimuth and altitude angles of the sun in summer, December, and winter in June, and in autumn, April. Accordingly, the following chart is devised, which allowed us to determine which side facade to control. For the purpose of the study, we will work with 3 scenarios in each season selected: 9 a.m., 12 p.m., and 3 p.m. Based on the calculated angles, the kinetic facade is opened and closed as follows.
Part 1. Summer.
The following results are displayed for scenario 1 to 3. For example, in December at 12 p.m., the base case reached 120 kilowatt and the improved case reached 58 kilowatt.
To measure the effects further, we have closed the shades completely and measured the effects of the solar gain.
We found further reductions in solar gain in scenarios 1 to 3, 50 kilowatts for scenarios 1 and 2, and 40 kilowatts in scenario 3. Air temperature reductions is also noted as follows: 17% reduction in scenario 1, 22% reduction in scenario 2, and 21% reduction in scenario 3.
In summer, for the lux contours, the illuminance level have decreased by 1,500 lux on floors and 900 lux in walls. Part 2. Autumn.
In autumn, we have also controlled the openings based on the angles. We have also found significant reductions in solar gains and air temperatures for scenarios 1 to 3. As an example, in scenario 1, April 9 a.m., in base case, the solar gain has reduced from 72 kilowatts to improved case at 40 kilowatts. For air temperatures, we have also noticed reductions for scenarios 1 to 3. As an example, in scenario 1, air temperature base case is at 30 and improved case is at 25 degrees.
In autumn, for the lux contours, the illuminance level have been decreased around 900 lux on walls and 1,000 lux in floors. Part 3. Winter.
In winter season, the openings are controlled according to determined angles.
We have noticed major reductions in solar gains and air temperatures for scenarios 1 to 3. As an example, for scenario 3, in June 3 p.m., solar gain for base case was at 29 kilowatts and improved case is at 17 kilowatts. Furthermore, the solar gain for a fully closed shade was also measured for scenarios 1 to 3 and found to have improvements. The air temperatures were also recorded for scenarios 1 to 3. For example, in scenario 2, June 12 p.m., at base case is 23 degrees Celsius and improved case is at 19 degrees Celsius.
In winter, for the lux contours, the illuminance levels have decreased around 600 lux in walls and 1,000 lux in floors.
In order to determine if our building is within the comfort zone according to ASHRAE, we generated the same for June, April, and December. Our findings shows that the comfort zone was achieved only in December, but not in April and June. For this reason, we decided to turn the HVAC on and observe the results.
For the improved case, we have reached the comfort zone with HVAC on in autumn and in winter.
With the HVAC turned on, it is important to measure the heating and cooling loads and how much the PV's generated electricity can be contributed based on the following results from the simulation. Results here shows the cooling loads in summer for the month of December. 31.7 total reduction in cooling loads, 20% total reduction in energy consumption, PV generated electricity 2,518.8 kilowatt per hour, 16% of total energy generated by PVs in summer.
The results shows the total cooling and heating loads in autumn for the month of April. 40.7% total reduction in cooling loads, 71.5% total reduction in heating loads, and 30.8% total reduction in energy consumption. PV generated electricity is 1,391.8 kilowatt per hour and 11% of total energy generated in April by the PVs.
The results here shows heating load in winter for the month of June. 34% total reduction in heating loads, 23% total reduction in energy consumption, 743 kilowatt per hour PV generated electricity, 3.8% of total energy generated in summer by PVs. The HVAC internal temperature set at 21 degrees, we have seen a reduction in solar gain. In December, 20% reduction at 9:30 a.m., 43% reduction at 12:30 p.m., 28% reduction at 3 p.m.
The most reduction was being at 12:30 p.m.
In autumn, the percentage reduction is 19% at 9:30 a.m., 38% at 12 p.m., and 28% at 3:30 p.m.
The most reduction was being at 12:30 p.m. In June, the percentage reduction is 25% at 9:30 a.m., 35% at 12:30 p.m., 28% at 3:30 p.m. The most reduction was being at 12:30 p.m.
In our study of the daylight factor, we see variations in daylight factor for December and June when comparing base case to improved case. Although the daylight factor is not within the comfort range of 2 to 5%, we have managed to reduce the base case by approximately 5% for summer and 2% in winter.
We have conducted CFD analysis for December 9 a.m. scenario to compare base case and improved case. For CFD analysis, we have noticed more improvement in the external simulations than in the internal. Although the internal simulation showed slight improvements, the external analysis showed more improvements in the velocity and the pressure.
As Australia's sustainability assessment method, the Green Star rating tool is used. The base case achieved a total of 44 credit points, giving it 3 stars, whereas the Kinetic case gained 69 points, mainly in the following categories: indoor environmental quality, energy, materials, and innovation. This awarded it 5 stars.
Moving to the next topic, which is life cycle analysis. First of all, what do we mean by life cycle analysis or assessment? Life cycle assessment involves the evaluation of some aspects of the project system through all stages of its life cycle to help in environmental management and longer-term and sustainable development. There are many softwares that can calculate the life cycle analysis of a building. One of them that's linked to the IES software is called One-Click Life Cycle Analysis. Let's show you now how we linked our model to the one-click life cycle analysis software. As you can see here on the screen, by selecting our model, we just click in the navigators and then we will have the one-click life cycle analysis. We just run the software in order to get the results. Here we will start importing our project by selecting our design and run the software again. Then we will get this data that shows all the material used in our project. As you can see here, we use steel roof with a quantity of 1,715 meters square per 2 mm. With running the project again, we can get other results. Life cycle analysis results, construction materials, building materials. As you can see here, the horizontal structures with having the quantity and the CO2 equivalent. Moving to the energy consumption, we got the number of 251 kilowatt hour from the IES simulation, building area, and the calculation period, which is 60 years depending on the maximum average of green star buildings. By running the software again, we can get some life cycle overview of global warming figures and the most contributing materials of global warming, such as the granite paving, isolation panel. Overall, as you can see here, we have 4 kg CO2 equivalent meter square per year. Let's run the results of the report. This is the report, and it will be submitted through hard copy within a while. At the end, as you can see, we got a rating of A within Green Star certification. As you can see here, we got 222 kg CO2 equivalent per meter square, 53% materials, 1% transportation, 43% replacement, and 4% end of life. To validate the results of our building, we compare it to others. As you can see, this building got 414 kg CO2 equivalent per meter square, 76% materials, 2% transportation, 19% replacement, and 4% end of life. Second example, we have it here in North America, which got a class of D with having 98% materials, 4% transportation, 4% replacement, and 3% end of life.